And welcome back to Mr. Gregorius Math. Today we're taking a look at algebraic inverses. So to figure out what an inverse is, we kind of have to have a function defined, and then we have to take advantage of something called the inverse identity. And the best example for the inverse identity is talking about something in a state and having a function that changes its state. So suppose I have my hand face down. The function could be flip. And the inverse function of flip would be flip back. So if I start in the down state and I flip and then flip back, I end up in the down state. If I start in the up state and I flip and flip back, I end up in the up state. The way that this looks algebraically is through something like this. We say that if we apply a function and the inverse to a particular state, then we're going to get back to the original state. In other words, if I start with my hand down and I flip it back and then I flip it again, I end up with my hand down. So that is the inverse identity. We can use this identity to come up with some algebraic definitions of inverse. So this is a key point here. We're going to keep this along. An identity is a useful tool for us. So suppose h of x is equal to the square root of x minus 1 plus 2. So if I wanted to find the inverse of h of x, I would need to find something that maps all the x points to all the y points. So all the points, their x and y coordinates, to the inverse of those. They would then become y and x coordinates. I can do this by applying the inverse identity. Now, since my function is not named f, it's named h, I'm going to write down my inverse identity in terms of h. So this would be h of h inverse of x is equal to x. And now we have to remember a little bit about function notation. So this middle h right here is the input into h. So it's going to go everywhere where I see an x. So to write down h of something, it's going to be the square root of something minus 1 plus 2 is equal to x. So essentially what I've done is I've just substituted my new input in place of x, and I've replaced that in my inverse identity. Now my goal from here is to solve for h inverse. So h inverse is just a function, and I'm trying to get it alone. So I'm going to remove all the pieces from it. My first piece is I'm going to subtract 2, and what I do to one side, I have to do to both. So I have x minus 2. That's the square root of h inverse of x minus 1. And then now I'm going to square both sides to get rid of the radical. So I'll have h inverse of x minus 1 is equal to x minus 2 squared. And then I'm going to add 1 to both sides, so I'll add 1. Those cancel. And I'll be left with h inverse of x is equal to square root of x minus 2 squared plus 1. So this is my inverse function. Now, interestingly enough, we had to recognize that there was a domain of this function. So the domain of this guy, if you recall back to radicals, it's anything that causes a negative number in here is outside of the domain. So 1 is valid because 1 minus 1 is 0, but anything less than 1 is not going to be valid. So my domain is x is greater than or equal to 1 and an element of the reals. And so that domain is going to create a particular range. And the range on this particular function, its smallest possible value is going to be when this is equal to 0. So 0 plus 2 is 2. So my range is y is greater than or equal to 2, and y is an element of the reals. Now, with my actual inverse function, you'll notice I have a quadratic. And if I did a quick sketch of this quadratic, it would look something like this. So I'd go over to 2, and I'd go up to 1, and I'd make my point, and it's a parabola that opens up. So I'll go over 1, up 1, over 1, up 1, over 1, up 3, over 1, up 3, and my quadratic would look like this. And I am going to draw dotted lines here. So that's what my inverse function would look like. My original function would have been this radical at that has its points been translated 1 to the right and 2 up. So 1 to the right and 2 up would be right here. And it's that radical that as we go over 1, we go up 1, and it would look like this. Now, it may become a little bit clearer now why I drew this other side in dots. Because this domain was restricted, I'm actually going to have a restricted domain and range of my inverse as well. So my domain and range of my original function will reciprocate, they'll flip, and I'll now have a domain of x is greater than or equal to 2, which I see here, going x is greater than or equal to 2, and a range of y is greater than or equal to 1, which I see here, going y is greater than or equal to 1. So when I apply my algebraic inverse rule, I have to keep in mind that it's going to flip the domain. I may not actually have the entire thing shown here. And that happens because of a little bit of a dance with complex numbers and having to remove a branch of the function at the end or at the beginning. If you do an inverse of a quadratic, you're going to end up getting a radical. And when you do that, you won't actually show the full reflection of both arms of the quadratic. You only see one of them. So you end up having to either restrict the domain or create a secondary function to map the other arm. So this step of finding inverses by using the inverse identity and then solving for h of x, it's consistent through all of them. Let's just do one more quick practice question so that we can see it happen fast with a different function type. So we're going to have our function be y equals, let's go 2 over x minus 1 plus 3. Now, you may notice that I don't have it in function notation right now. That's okay. I can keep in mind that what ends up happening here is I end up replacing the x value with a y value. So a common trick you see for inverses is when you have your function given in this way, your first step isn't use the inverse identity, it's switch out your x's and y's. This is exactly the same thing we would have had we used the inverse identity, except for the fact that this would have been x equals, and then this would have been inverse of some function notation. So now we go ahead and instead of solving for the inverse function, we just solve for y, and that will give us our inverse function. So I'll subtract 3 from both sides. And I'm going to either reciprocate both fractions or I'm going to multiply both sides by y minus 1. So I'll have y minus 1 times x minus 3 is equal to 2. Now I'm going to divide both sides by x minus 3. And lastly, I'm going to add 1 to both sides. And so this is my original function, and this is the function's inverse. So I exchange x and y, then I solve for the inverse. I hope that was helpful, and I wish you good luck in finding your functions and all their inverses. May every inverse be a function, but not every inverse is actually a function. Join us next time on Mr. Grower's Math, and don't forget to hit like, subscribe, and ring that notification bell.